All right, everybody, good afternoon. Welcome to our first language modeling session. Obviously, if you're at EMNLP, this is the session to be at, so we've got a great show for you. So our first speakers are going to be Elman and Jason from NYU.
Hi, everyone. Thanks for coming. I'm Elman, and we're going to be talking about the work on non-autoregressive neural sequence modeling by Iterative Refinement, the work with Jason and Kyung-Yun. So before I start talking about non-autoregressive sequence modeling, I'm going to quickly go over autoregressive modeling. And the main idea behind autoregressive model is to model the probability of the sequence X as the product of the conditional distributions, where the probability of the token at time step t depends on all the previously generated tokens at the previous time steps, as shown on this formula. And similarly, in the conditional case, we condition the probability on the source sequence X. And autoregressive models, especially the models, the LSTMs with attention, have proven to be a very strong baseline on many sequence-to-sequence problems. And as shown on this slide, this is one successful example of Google's machine translation system. However, there are two main challenges with RNN-based models that it's not possible to overcome due to its nature. The first challenge is that it's not possible to parallelize the forward and backward pass during testing and decoding, because in order to calculate the hidden activations at time step t, we have to calculate all the hidden activations at the previous time steps during the recurrence. And over the last 2-3 years, we've seen a lot of great models, mainly convolutional based and fully attentional based, that completely eliminate the recurrent connections and allow us to parallelize the training and significantly improve the convergence speed of the models. Although one thing that is common to all of these models is that it's not possible to parallelize the decoding at the test time due to autoregressive nature of all these models. That is, kind of in order to generate each token, we have to wait for all the previous tokens to be generated, and the process becomes sequential. And that's where the non-autoregressive models come in. And effectively, the idea behind the non-autoregressive modeling is to model the probability of the sequence X as the product of the independent distributions. That is, the probability of the token at time step t is independent from all the other tokens. And that allows us to generate each token independently in parallel without waiting for all other tokens to be generated. And similarly, in the conditional case, we condition each of the probability distributions of the token on the source sequence X. Now, the problem is, how do we capture the dependencies among the target variables? Well, in the autoregressive case, the dependencies are modeled implicitly because the token at the time step t is conditioned on all the previously generated tokens, whereas in this case, we don't have any conditional dependencies among the output tokens. And our solution is to introduce the set of latent variables that are supposed to capture those dependencies among the target variables. And because of the complex dependencies among the target variables, we don't just add one set of latent variables, we introduce the set of L intermediate latent variables. And within each set of latent variables, they're independent of each other. However, when we generate the Lth set of latent variables, we condition it on the previously generated set of latent variables, as shown on this formula before. And in this formula, you can see the expression of the new probability distribution of target sequence Y conditioned on the source sequence X. Well, now the challenge is in training those latent variable models, which is very complicated and very hard. And the way we ease this optimization procedure is by constraining those latent variables to be of the same type as the target sequence. So for example, if we do machine translation from French to English, so each set of latent variables becomes the English sentence that we're translating to. And now the task of generating those L intermediate latent variables intuitively becomes the task of refining our target sequence L times before we generate the final target sequence. And this allows us to use just a simple supervised optimization in order to train those latent variables. So effectively, at each refinement step, we just simply minimize the cross entropy between that intermediate sequence that is generated and the ground truth sequence Y. Now, another way to look into our model, by kind of like interpreting it through iterative refinement lens, is by looking at each iteration of the refinement as denoising the noisy version of the target sequence. And what this primarily allows us to do is, in addition to using the models generation at each refinement step, is we can artificially corrupt the target sequence ourselves and pass it to the model to refine it. And effectively, training this denoising autoencoder is also very simple, and it's just simply done by, again, minimizing the cross entropy between the ground truth and the generated target sequence. And what in fact worked best in practice for us is mixing those both objectives. That is, at each refinement step, we randomly decide with probability alpha whether to use the model's own generations and pass it to refine at the next step, or just to use the artificially corrupted data and pass it to model to refine. So before Jason starts talking more about the model architecture and the experimental results, one procedure that allowed us to almost bridge the gap between non-autoregressive models and autoregressive models is distillation. That is, instead of using actual targets from the data set, what we do is we train a good autoregressive models and then use the generations from this autoregressive models as the target to our non-autoregressive model. And what we found that it allowed us to improve performance by absolute margin of 10 to 15%. So yeah, now Jason's going to talk more about architecture and experimental results.
Hi, I'm Jason. So here's our architecture. So right off the bat, it's based on the transformer model, except we have 2 decoders instead of 1. And the reason why is that the first decoder takes the source sentence and produces a rough translation in the target language. And then the second decoder takes that rough translation and keeps refining it until we get it right. So to run you through step by step, we first encode the source sentence using a standard transformer encoder. And then at the end, we predict the length of the target sequence, which is only used during decoding. During training time, we still use the ground truth reference length. And we use the same source embeddings as input to the first decoder. And in doing so, we either repeat or drop a few tokens to make sure the length is the same. And after n layers of transformer decoder, we have pre-softmax hidden states from which we either sample or argmax to get the predictions. And then we take the embeddings of those predictions and we add that to the pre-softmax hidden states to give us the input to the next iteration. So what adding the two allows us to do is it allows the gradients to flow across iterations. So we just apply the second decoder many times. During training, we use this 3 times. But what we found to work well during inference time is just to keep running the second decoder until the output stops changing. So we call this adaptive decoding scheme. And we found this to give a good balance between performance and speed. So our total loss is the sum of our usual cross-entropy loss, summed across k iterations, along with the target length prediction loss. So we experimented with 3 MT datasets and 1 image captioning dataset. And this is the IWSLT results. And let me explain what these 4 columns mean. So the first column is the English to German BLEU score. Second is the German to English BLEU score. And then the last 2 columns are the decoding speed on GPU and CPU measured in tokens per second. So all these numbers, higher the better. So comparing with the autoregressive transformer baseline with beamwidth 4, our model with adaptive decoding scheme gives 93% of performance while giving 2 times faster. So quite promising. And we see this result across different tasks and different language pairs. So on English to Romanian, our models is 2.7 times faster. And on English to German, WMT, our model is 2.4 times faster. And similar results with MS COCO, image captioning. So where do all these gains come from? We ablated against a few things. So the first column is the number of refinement steps used in training. The second column is how often do we use the denoising autoencoder objective. And the third column is whether or not we use distillation. So we made a few observations here, and we get improvement in BLEU score with more iterations used in training. And secondly, mixing the 2 learning objectives give us the best gains. And then thirdly, similarly to previous works, sequence-level distillation we found crucial to match performance with the autoregressive models. So here we show how decoding latency changes with respect to sentence length. So the top 2 plots are the autoregressive baselines, and we show that decoding from autoregressive models takes longer if you have longer sentences, unsurprisingly so. In contrast, though, with our non-autoregressive models, the decoding time is fixed regardless of the length. And then we show improvement in BLEU score if we decode up to 100 iterations during inference time, which is a lot more than 4 iterations we use in training, but we still see the performance gains. So looking at a few qualitative examples, we see that across the board, our model generally modifies hypothesis closer to the reference sentence. So looking at the second example, the first decoder produced the phrase, "the news were usually depressing," and then the second decoder immediately drops the were and gradually refines it to something that sounds more natural. So the news was mostly depressing. Similarly, with the phrase "unusual at the time," our model gradually forms that phrase word by word. With image captioning, similarly, we see that our model gradually, incrementally captures more detail about the image. So what used to be just a yellow bus in the first iteration gets refined to a yellow and a black bus, and the parking road becomes a parking lot. So in a nutshell, we claim that our non-autoregressive model is a good balance, strikes a good balance between performance and speed, especially if you care more about speed. However, there are still a few limitations, such as we still need sequence-level distillation to match that performance. So our training is still not end-to-end, and then maybe we might need a better architecture, better suited for non-autoregressive models. So that's it, and thank you so much.
Hi, thanks for the nice talk. I'm Yunsu Kim from Aachen, Germany. Have you tried your approach on normal autoregressive models? Because I'm worrying that the autoregressive models already considers a bit of target history, so this kind of iterative refinement work less than the non-autoregressive case.
I'm aware that that approach has been proposed before. So using iterative refinement on autoregressive case. So I think on that paper, this was NIPS, I think 2 years ago. It was shown to give better performance, but it will take longer, even longer than just one decoding pass with autoregressive models. So our claim was make it faster.
But do you have your own experience on that?
We haven't tried it ourselves. Yeah.
Okay, thanks.
Thanks.
All right, I'd like to ask a question. So this is an interesting, very practical way to train a model that has effectively stacks of latent variables in it. But how deep do you think you would need one of these things if you, say, just learned the latent variables, even if they were, say, discrete symbols in a vocabulary of roughly this size? Would you be able to capture, say, good translations in just 2 layers of this kind of thing if you were actually optimizing, say, the marginal likelihood of the translation probabilities without this constraint that sort of the first layer was trying to also look like the final translation? So you relaxed effectively that constraint.
Yeah, I doubt that 2 layers would be enough. So in our experiments, we try to fit as large of a model as we can. And due to GPU constraints, probably it would be better if it was deeper and bigger.
Well, I guess one question is actually, does this representation actually allow, so we talked a bit offline before this, but in theory, we know that given enough capacity, an autoregressive model can capture any distribution. Do you think, I guess one question is, would a 2-layer model without constraints on what the latent variables capture in the lower level, so if they had enough capacity, do you conjecture that it would be capable of matching any distribution?
I don't know. So I feel like we need a more detailed investigation to answer this question.
Hi, thanks for the talk. I was wondering, does the model has the potential to oscillate between translations at the different layers? Or is there any kind of mechanism that prevents it from correcting back and forth? And do you observe that if that's the case?
I think that's something that we did observe, especially with the denoising autoencoder objective. Because some of the corruption functions that we used is insertion, switching, removal. We did actually find that in the qualitative examples that we saw, over across iterations, a model would add a word and then remove it and then add a word. So it is a thing. But looking at the general BLUE score, overall, it does tend to sort of refine the hypothesis gradually towards the reference sentence. So didn't seem to affect too much towards the BLUE score, yeah.
Thank you.
Thanks.
All right, let's thank our speakers again.